Hello, I am Dr. Shigar Kanti, Associate Professor of Mathematics, Government First Grade College, KR from Bangalore. In this video, I am going to discuss some basic concepts of graph theory. I will consider a problem which is known as Koenigsberg bridge problem. Koenigsberg bridge problem. The problem is nothing but this is a river, okay, and one island is here, I1. Another island is here, I2. This is the bank of the river 1, B1, and this is the bank of the river B2. So here we have, this is one bridge connecting B1 and I1, and this is the second bridge connecting B1 and I1, and this is the bridge connecting I1, B2, one more bridge connecting I1, B2, and there is a bridge connecting B1 I2, one more bridge connecting B2 I2, and one more bridge is here connecting I1 and I2. So that is here we have four land areas, that is the bank of the river 1 B1, bank of the river 2 B2, and two islands I1 and I2. And these four land areas connected by some bridges, totally 7 bridges are here. My problem is I am somewhere here, maybe on B1 or I1 or B2 or I2. I am somewhere here. I want to cross all the bridges once and only once. That is no repetition of bridges. I want to cross all the bridges without repetitions and coming back to the same point where I have started my journey. If I start from B1, I have to cross all those bridges once and only once, and I have to come back to the same point on B1. This is the Koenigsberg bridge problem. The Swiss mathematician Euler was thinking on this problem. What he did, instead of going like this in this figure, he represented the land areas by the points and the corresponding the bridges by the lines joining the corresponding points. So that is here. What he did, he takes this B1 one point, and this is I1, the island one point, and bank of the river B2 another point, and one more island is here, this I2 by 1 point. That is here. These four land areas represented by 4 points. And here the corresponding bridges. There are two bridges joining B1 and I1. So that is he joined B1 and I1 by two lines. And there are two bridges joining I1 and B2. So that is two lines joining I1 and B2. One bridge is between I1 and I2. So that is one line joining I1 and I2. And one bridge joining B1 and I2. So that is B1 and I2. And then one more bridge is joining B2 and I2. Okay. So that is here. This figure can be converted into this figure, and he called this as a graph. And by defining the graph, he became the father of graph theory. Euler became the father of graph theory. Okay, so he tried on this graph. Okay, so then what is a graph? How we define a graph? So and the problem is this cannot be solved because of some constraints are there here. It is not possible to solve. Okay, so this is known as Koenigsberg bridge problem. He defined a graph. Then what is a graph? Graph is nothing but 1 point, 2 point, 3 point, 4 point. But that is basically points must be there. And some lines are there that is joining the corresponding some points here. Okay, joining the points. So that is the graph is nothing but set of points and the set of lines. Okay, and every line joining 2 points here. So therefore we can define a graph G as a uh, uh, set, that is non-empty set V called the vertex set, that is the points here. Okay, points together with the set of edges. So that is, let me denote that by say E. Every member of E is said to join two members of V. Then this is the definition of a graph. So how we define the graph? So I am going to define the graph. I'll go to the next page. What is a graph? Definition of a graph. A graph is a non-empty set V together with the set E, and this may be empty. Okay, may be empty. The set may be empty. So here V is called vertex set, and E is called edge set. Okay, E is called edge set, and here every member of E is said to join two members of V. So that is, this E is nothing but E is the set of unordered pairs of the elements of V. Okay, unordered pair. So that is, for example, I will write and is denoted by, notation is like this, and is denoted by G equal to, usually we write like this. Okay, V comma E. V is the vertex set and E is the edge set. Let me consider an example. V equal to say 1, 2, 3, 4, 5. Okay, V equal to 1, 2, 3, 4, 5. And E equal to, here, this is the edge set. This is nothing but the pairs of the elements of V, unordered pairs. That is, unordered pairs means 1, if I write 1 comma 2, it is same as 2 comma 1. So that is here 1 comma 2, 2 comma 4, 3 comma 5, 4 comma 1, 5 comma 2. Okay, like this. This is the edge set. Then if I write G equal to VE, this is defined as, this is nothing but a graph here. And we can represent this in pictorial form. So that is here, I will represent the elements of V by the points, okay, and the elements of E by the lines. So that is, how many points are here? 1, 2, 3, 4, 5. Let me denote them by, this is 1, this is 2, this is 3, and this is 4, this is 5. Okay, I have represented the elements of V by points. And next, these are the pairs here, 1, 2. 1, 2 is there. That means I have to join 1 and 2. This is an edge. And 2, 4 is there. So I will join 2, 4. And next 3, 5 is there. So I will join these 2 points here. 3, 5. And 4, 1. 4, 1 is there. I will join this 4, 1 or 1, 4. Both are same here. 4, 1. And 5, 2. 5, 2. Okay. So this is the graph, and we can write this graph by like this also. So first I will write 1, 2, 4. This is a triangle. I'll write this as, this is same as 1, 2, 4. Okay. So if you observe here in this figure, 1, 2, 4. This is a triangle. And then 2 to 5, 5 to 3. 2 to 5, 2 to 5, 5 to 3. Both are same here. So that is here. These two looks different, but they are same. Here the adjacency is important. This see here, one is joined with 2, 2 with 4, 4 with 1. Here also 1 with 2, 2 with 4, 4 with 1. And then 2 with 5. Here also we have 2 with 5. 5 with 3. So 5 with 3. So these two are same graphs here. Okay, this is a graph. We can draw many graphs here. I'll draw some more graphs. G equal to, this is in the pictorial form. Okay, this is a graph. So that is your graph is nothing but vertices and the edges. Okay. So here we have considered some graphs here. We have points. I have considered the graph with more than 1 point. Suppose it has only 1 point, then you say that it is a trivial graph. So that is here. Trivial graph is nothing but a graph with only 1 point, or one vertex is called trivial graph, and consequently there will not be any edges here. So that is here, trivial graph is just a point, only 1 point is there, no edges are there. So here S set is empty and the vertex set consisting of only one vertex. This is known as trivial graph. And what about non-trivial? Non-trivial is a graph with more than one vertex. So that minimum two vertices is called a non-trivial graph. So that is here a graph with at least two vertices. At least two vertices is called a non-trivial graph. Okay. 2, 3, 4. If with only 1 point, it is a trivial. More than 1 point, it is known as a non-trivial graph. Okay. And next we define null graph, or we call it as sometimes empty graph also. Empty graph. So here in trivial graph we have only one vertex. Non-trivial minimum two vertices. So null graph is nothing but a graph without edges. Okay, null graph is nothing but a graph without edges. That is edge set is empty set, then you say that it is a null graph or empty graph. Sometimes we say that it is a totally disconnected graph. So that is here a graph with a graph. We write say g equal to b comma e. A graph g equal to b comma e is said to be null graph if h set is equal to empty. That is without edges. If there are no edges, then you say that it is a null graph or empty graph. Okay. If we go for adjacency. Adjacency. So here let me consider a graph. Let G be a graph like this. This is a graph. So this is say 1, 2, 3, 4, 5. Okay. Now here 1 comma 2 belongs to edge set of G. This is an edge here, okay, because 1 2 is an edge here. And suppose there is an edge, 1 2 is an edge, then we say that 1 and 2 are adjacent to each other. That is here 2 vertices are said to be each other, adjacent to each other if there is an edge joining these two vertices. So that is here 1 is adjacent to 1 is adjacent to 2. Similar conversely, we say that 2 is also adjacent to 1. And is 1 is adjacent to 3? Yes. Is 1 is adjacent to 4? No. Because there is no edge joining 1 and 4. Okay. 1 is not adjacent. 1 is not adjacent with 4. Is 1 adjacent with 5? No. Because there is no edge joining 1 and 5. So therefore 1 is not adjacent with 5. And 4 is adjacent with 5. Yes, I think, because here there is an edge joining 4 and 5. 3 is adjacent with 4. Okay, 2 adjacent with 3, right? So this is the adjacency of the vertices. And then we define incidency. So here let E equal to U comma V be an edge of a graph say G. So that means here it's like this. U vertex is here, V is here, E is here. In this case, we say that, so here U and V are adjacent to each other. And E is an edge joining these two vertices, U and V. In such case, we say that E is incident with U as well as E is incident with V. Or we say that E is incident with U and V. And we say that U and V are incident with E. So this is incidency. So that is here E is incident with U. Similarly, E is incident with V, and V is incident with E. UV is also incident with E. Okay, this is incidency. So that is here adjacency. In the term comes adjacency, it is between the two vertices. Incidency comes, it is between a vertex and an edge. Now we consider one more example, an incidence. Suppose we have this is a graph. 1, 2, 3, 4. This is our E1, E2, E3, E4. Now here we say that E1 is incident with E1 is incident with 1 and 2. Okay. E2 is incident with 1 and 3. Right. Because E2 is U1 and 3, there is a line joining U1 and 1 and 3. E2 is the line joining 1 and 3. Therefore, we say that E2 is incident with 1 and 3. And E3 is incident with 2 and 3. E4 is incident with 3 and 4. Okay. This is about the incidency. Incidency comes between a vertex and an edge. Okay. Now, as we have defined the adjacency of the vertices, similarly we can define the adjacency of the edges. How we define? Suppose in this same graph, if I consider this graph itself, see here E1 and E2, there is a common vertex here. So that is your E1 and E2 are incident with a common vertex. Then we say that E1 and E2 are adjacent to each other. Similarly, E1 and E3 are incident with a common vertex 2. Then we say that E1 and E3 are adjacent. E2 and E3 are adjacent because they are incident with common vertex 3. E1, E2 adjacent, E3, E4 adjacent, E2, E4 are also adjacent. But here E1 is not adjacent with E4. Okay, because there is no vertex common between E1 and E4. So that is here we define two edges, say E1 and E2 are said to be adjacent if there is a vertex common to E1 and E2. So that is, so vertex say U I will write here. So that means here that is E1 incident with U, E2 also incident with U. If there is a vertex common such that these two edges are incident with that vertex, then you say that these two edges are adjacent. Okay, so this is adjacency of the edges. In this example, E1, E2 adjacent, E1, E3 adjacent, E2, E3, E4 adjacent, but here E1 and E4 are not adjacent, right? This is about the adjacency of the edges. Now we define degree. We define, just a minute. Okay. Degree. Degree of a vertex. Degree of a vertex. How we define the degree of a vertex? The degree of a vertex, say U, uh, is defined as the number of edges incident with U. Okay, I will go to an example. G. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8. This is a graph with 8 vertices. Now we write degree of 1 is, degree of 1 is this vertex here. How many edges are incident with 1 here? 1 edge, 2 edge, 3 edge. Therefore, degree of 1 equal to 3. What about degree of 2? 2 is here. Here also 1 edge, 2 edge, 3 edge. That is 3 edges are incident. Therefore, its degree is equal to 3. And coming to vertex 3. This vertex 3 is incident with only 1 edge. Therefore, its degree equal to 1. Coming to 4. Degree of 4. This is also equal to 1 because this is incident with only 1 vertex. And coming to 5. 5. This is incident with 1, 2, 3, 4. So therefore, degree of the vertex 5 is equal to 4. Coming to degree of 6 here. This vertex 6 is incident with 3 edges. Therefore, its degree is 3. Coming to 7. Okay. 7. This vertex is incident only 1 edge. Therefore, its degree is 1. And 8. This is incident with 2 edges here. So therefore, its degree is equal to 2. Okay. How many vertices are here? Totally 8 vertices are here, right? And what is the sum of the degrees here? Sum of the degrees, 3 plus 3 6 plus 1 7 plus 1 8, 8 plus 4 is 12. 12 plus 3 is 15. Degree of 1, 2, 3, 4, 5, 6, 7, 8. Okay, 3 plus 3 6, 7, 8, 12, 12, 15. This is 15. 15. I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8. The degree of 1 equal to 3. Degree of 2 is also equal to 3. Degree of 3 is 1. Okay. How many? What is the sum of the degrees here? 3 plus 3, 6, 7, 8 to 12, 15, 15, 16, 7, 18. Okay. This is the sum of the degrees. And how many edges are here if I count? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges are here. Okay. 9 edges are here. Sum of the degree is equal to 18 and the number of edges is equal to 9. Can we find a relation between the sum of the degrees and number of edges? Okay, let me consider another example. One more example. Say G1. This is the graph. And what is the sum of this vertex? Degree of this vertex 1. Degree of this vertex is 2. Degree of this vertex is 1. What is the sum of the degrees here? 1 plus 2 plus 1, this is equal to 4. And what are the number of edges here? So here we have 2 edges are there. So here sum of the degrees is 4 and number of edges equal to 2. I will consider one more example. This is the example. See here, this is 1, 2, 3, 4, 5 and totally 6 vertices are here. Degree of these vertices 1 plus 1, 2, 3, 4, 5. Plus here 1, 2, 3, 4, 5. Degree of this vertex equal to 5 and here we have degree of this is 1 plus 1 plus 2, 3, 4, 5 plus 5, that is 10. Degree of sum of the degree is equal to 10 and how many edges are here? 1, 2, 3, 4, 5. Okay, 5 edges are there. So that is here. See 4, sum of the degree is equal to 4, 2 is the number of edges. Sum of the degree is equal to 10, 5 is the number of edges. Okay. And here in this case also, sum of the degree is equal to 18, number of edges is equal to 9. That means here sum of the degree is twice the number of edges here. In second example also, see, sum of the degree is equal to twice the number of edges. Here also, sum of the degree is equal to twice the number of edges. So that means here, we observe that sum of the degrees is equal to 2 into number of edges. Can you prove this result? Yes, I think we can prove. See here, how to prove this? See, this is an edge E and U, V. Two vertices are there. What is the degree of U? 1. What is the degree of V? It is equal to 1. And here one edge is there. This edge is incident with U as well as incident with V. So that means here every edge is incident with 2 vertices. Exactly 2 vertices. And this edge contributes 1 to the degree of U and 1 to degree of this V. Suppose one more edge is there. Okay. So this is if I take E1 and if I take this E2. See here E1 contributes 1 degree to U, 1 degree to V. This contributes 2. And E2 contributes 1 degree to V and 1 degree to W. So that means here one edge contributes 2 to the sum of the degrees. 2 edges contribute 2 to the sum of the degrees. 3 edges contributes 1 edge contributes 2, 2 edges contributes 2 plus 2, 4 to the sum of the degrees. And if I have 3 edges, then it contributes 6 to the sum of the degrees. So therefore, if say q edges are there, then it contributes twice q, that is 2 into q, to the sum of the degrees. So that we can write like this: one edge contributes to the sum of the degrees. Okay, because this is the incident with uh, two vertices, and suppose two edges are there, contributes 4 to the sum of the degrees, and three edges are there, it contributes 6 to the sum of the degrees. Four edges contributes 8 to the sum of the degrees, and in general say q edges are there, then it contributes twice q to the sum of the degrees. So that is here sum of the degrees equal to twice the number of edges. So we write this like this, that is that is sum of degree of say vi, this is equal to twice the number of edges. So this is the first theorem in graph theory. Sum of the degrees of the vertices equal to twice the number of edges.